So far with the scaling arguments and the assumptions that we've made, we have this as an intermediate step in deriving our QG vector momentum equation. We've applied scaling arguments to the acceleration term on the left. We've applied scaling arguments to the horizontal advection term. We scaled the vertical advection term and actually eliminated it completely from the equation. And we now turn our attention to the Coriolis term here on the far right. We recognize that f, the Coriolis parameter, which is 2 times the rotation rate of the Earth times the sine of latitude, varies with latitude. That is, f is a function of y. So f will change with y. However, it goes with the sine of latitude, which is complex. We'd like to be able to take the sine function and turn it into something a little bit easier and linearize f and get rid of that sine dependence. And so we do that by invoking a Taylor series approximation. So we'll center our QG domain at 45 degrees, which is a good mid-latitude value. We'll let y equal 0 there, and then we will apply the basic form of the Taylor series to this particular situation. So from calculus, here's the basic form of the Taylor series, and for our specific situation, here we're differentiating with respect to y, and we're letting a be 0 at our 45-degree latitude. So f at a becomes f at 0, and then we get on the right-hand side, f at a becomes f at 0 again. And then we're differentiating for our first derivative of f, we're differentiating with respect to y. And I've written this as a partial f partial y to be consistent with the Lachman text. And that's divided by 1 factorial, and then multiplied by y minus 0, since a is 0. For the next term, we have the second derivative of f with respect to y, divided by 2 factorial times y minus 0 squared. And then, of course, we have higher order terms, which we won't worry about over here. So we can go one more step down and rewrite these terms a little bit simpler over here. First of all, for the first time here, we write f at 0, we write it as f naught. So our f value that we are computing at 45 degrees latitude is going to take the special symbol f naught there. So this is our kind of base value for the Coriolis parameter centered at 45 degrees. For the second term, partial f over partial y divided by 1 factorial. 1 factorial is 1, so this just becomes partial f partial y, and then y minus 0 just becomes y. For the next term, partial squared f over partial y squared divided by 2 factorial. 2 factorial is just 2, and so we can write this term as partial squared f partial y squared times y squared divided by 2. And then we'd have these higher order terms that we don't care about. In fact, not only do we not care about the higher order terms, we actually are going to throw out the second order partial derivative here as well, and we're only going to retain the first 2 terms on the right-hand side. So we have f naught plus this partial f partial y times y. And this change in f with respect to y is, by definition, beta, so the variation of the Coriolis parameter with latitude. And so we rewrite this as f is equal to f naught plus beta y. And to determine the relative importance of these terms, we would need to do some scaling on our beta y term here. And to do that, we recognize beta is the change in f with respect to y. And we recognize also that f, if you compute it, varies roughly about, to a first approximation, 10 to the power of minus 5 is the variance of f over a synoptic meridional distance of about 1,000 kilometers. I figured this by computing f at 40 degrees latitude and computing f again at 50 degrees latitude, which gives you, to a first order of magnitude, about 10 to the minus 5. Now, the horizontal distance between 40 and 50 degrees is not exactly 1,000 kilometers. It's more than that. But to a first order of magnitude, that's to the closest order of magnitude, that's about correct. So using those variations, the variation of f 10 to the minus 5 and the variation of meridional distance of 1,000 kilometers, we can rewrite the change in f over change in y as 10 to the minus 5 over 10 to the positive 6, which gives us a scale for beta of 10 to the power of minus 11. So applying the scaling to f here, f naught goes as f, beta goes as beta, and y, the scale of y, goes as the horizontal length scale L. And we know all of these values. So f will go as 10 to the minus 4, beta 10 to the minus 11, which we just computed, and the horizontal length scale 10 to the 6, or 1,000 kilometers. So when you work out the scales here, we get 10 to the minus 4 for f naught, and we get 10 to the minus 5 for beta y, which suggests at first glance that we could probably ignore beta y out of this. However, there are very, very important dynamic consequences of allowing f to vary over synoptic distances. For one, this allows or supports the development of Rossby waves and retains the essential dynamics of Rossby waves, among other things. And so we don't want to throw out the fact that f varies with latitude. So we're going to retain the beta y term, even though it's an order of magnitude roughly smaller than f naught. So we'll include it due to variation of f on the synoptic scale, which again has very important dynamic consequences for supporting Rossby waves, among other things. So what this has become, this part highlighted here in blue, where we're replacing f with f naught plus beta y, this becomes a so-called beta plane approximation. Effectively, we're allowing f to vary, which retains the fundamental dynamics, but we've simplified by holding the change in f constant over our domain. So instead we've turned a sine function, which is nonlinear, into a linear polynomial here, f naught plus beta y, using the Taylor series. So this is a linearization of f. And not only does this retain the essential dynamics and simplify the math, but holding beta constant will also prove very useful, as you'll see a little later, as we derive the QG vorticity equation. To visualize this as a final parting shot here, recognizing that f goes as the sine of latitude, we can picture f as a portion of a sine wave from 90 degrees south to 90 degrees north, where f is 0 at the equator, reaches a maximum negative value at the south pole and a maximum positive value at the north pole. And we recognize here that we're using a mid-latitude value of 45 degrees. So you can visualize the beta plane. Instead of f varying non-linearly, we can visualize f varying linearly using this beta plane here at 45 degrees. So we're allowing f to change from lower latitudes to higher latitudes, but that change is happening at a linear rate as opposed to happening at a sinusoidal rate. So as long as we don't stray too far from 45 degrees, either south or north of there, the value of f is going to be pretty close to the real value, so comparing the pink to the green. So this works, again, as long as we don't go too far away from that latitude where we're centering our domain.